in this video, we're focusing on rates of change. So this is a more practical aspect of differentiation in calculus. So if you may have already known or know of the average rate of change, it's just your gradient formula that we've used. It requires 2 points, y2 minus y1 over x2 minus x1. So wherever you see an average between 2 points or 2 times or something like that, you know you're going to be using the gradient formula. Now, if a question mentions instantaneous rate of change, that's where we can use the gradient function. So we differentiate the function, and then we know to find the instantaneous rate of change by just substituting in a time value. So we're going to do an example here. So the number of bacteria in a culture increases according to the function b equals 2t to the power of 4 minus t to the power of 2 plus 2000, where t is in time in hours. So we need to find the number of bacteria initially. So whenever you see the word initially, over here, initially, we know that that means when time equals 0. So we can use that now to substitute into our formula. So if we have b equals 2 times 0 to the power of 4 minus 0 squared plus 2000, we end up with 2000. So the number of bacteria initially, before anything begins, is 2000. Now we have a question here. We need to find the average rate of change in bacteria between 2 and 3 hours. So the key word here was average, so I know I'm going to be using coordinates. So when I know that, I have 2 here. I have a 2 and a 3. We have our time value, but we do need to find our bacteria value. So what we're going to do is we're going to say let t equal 2. So that means my bacteria is going to be 2 times 2 to the power of 4 minus 2 squared plus 2000, which ends up equaling 2028. And then I need to do the same for let t equal 3. So b is going to equal 2 times 3 to the power of 4, take away 2, take away 3 squared times 2000, and that ends up being 2153. Okay, so we have our values there. So we know essentially our coordinates that we have are 2 and 2028, and then we have 3 and 2153. So we're going to go and use our m equals y2 minus y1 over x2 minus x1. So we end up getting 2153 minus 2028 all over 3 take away 1, which ends up equaling 125. And it's important here, because it is a rate, we need units, and we know it's bacteria per hour because that's what our x's and y's are. Our y's were the bacteria and our x's were time. So it's bacteria per hour. All right. The next thing, the rate at which the number of bacteria is increasing after 5 hours. All right, so because it's only given us after 5 hours, we know it's going to be an instantaneous one. So I know that I need to write down my formula first, and then we're going to differentiate it. So b equals 2t to the power of 4 minus t squared, plus 2000. All right. So now that we've done that, we need to differentiate it. So db, because that was what came first, over dt. So the 4 here comes out the front, and the 2 comes out the front here. The 2000, because it doesn't have a t value, is going to disappear. So we end up with 8t to the power of 3, because you minus 1 off the power, minus 2t, because you minus 1 off the power, we're left with 1. All right, so at this point is where we're going to use our 5 hours. So we need to say let t equal 5. So we have 8 times 5 cubed minus 2 times 5. And we end up with 990. Now again, it's a rate, so we need to make sure we have our units. So bacteria per hour. Now, we don't always use it in this. We also use it in terms of displacement, velocity, and acceleration. So if you don't know what those are, displacement is just the measure measures the distance of an object from a fixed origin, so whether it moves forward, back, away, left, right. It's that measurement from a certain point. Velocity is the rate of change of displacement with respect to time, and involves speed and direction. So again, acceleration is similar to that. It's the differentiation of v. So essentially, if you're given some sort of a displacement value, right, an equation, you can differentiate that to get the velocity equation, which you can then differentiate that to find the acceleration equation. So here we have an example. A ball rolls down a ramp, so that its displacement x centimeters in t seconds is 16 minus t squared. So I'm going to write that out first. So x equals 16 minus t squared. Now it's asking to find its initial displacement. Because it's x, I already know we're dealing with displacement, so I don't need to do any differentiation. And because it says initial, I know that time equals 0. So equals 16 minus 0 squared. So I know it's 16. We have an initial displacement of 16 centimeters because that is what it told us up here. And the next one is find its velocity when t equals 3. So I want to write this out again. I want to differentiate this because we want to deal with velocity. And I know that if x equals displacement dx over dt equals velocity, so the differentiation, and then over dt squared is acceleration. Now what that means is this just involves a second differentiate. You're differentiating the already differentiated function to get acceleration. So over here, 16 equals 6, x equals 16 minus 2. We're going to differentiate that to get dx over dt. The 16 disappears because it doesn't have any x's with it. The 2 up here comes out the front, and the negative stays, so it's negative 2t. All right. Then we want to say let t equal 3. So here we get dx over dt, or v equals negative 2 times 3, which is negative 6. And it does have units. Remember, it was in centimeters per second.